Hi, good evening, everyone. So let's start our class. Annotation. Okay. Okay. So in the last lecture, we started the logistic regression. So here, let's first give a brief review. I believe I stopped here in the summary, which is good. Okay. So the original idea is that I want to, include the idea of linear regression. Oh, sorry, I should say the opposite. I want to include the idea of probability theory, probability into linear regression. The difficulty is that for probability, for something, the probability must be between 0 and 1. I cannot have a probability, for example, 1.3. It doesn't make sense. But for linear regression, excuse me, for linear regression, in most cases, my y, which is my response part, the domain is R, the whole R line, real number line. So to this end, we try to we try to plug in this one, which is the log of two probabilities, Px and Qx. So by maybe junior school or high school, mathematics, we know this one belongs to the whole R. And in this case, I can formulate, I can I can include the idea of probability into linear regression. And then let me directly move here. So we're gonna build the model in this way. Here I use ym to be the reference, and this is actually all in one, all to one, all against the one model. Later in SVM support vector machine, you will see it. And then you can see for all other class, for y equal to 1 till 1 over m, I have totally such m equations, which is for each y equal to I given x equal to x over this y equal to m, where this one is the reference, then have the log of them equal to this beta I0 plus beta IT x. Be careful here. These betas are, and also these axes are all vectors. And again, what we want to get are these. I guess I can directly draw. Yeah, are these beta I0 and the beta I, the vector beta I. For x, I've known it. I don't have to, I don't have to ask what is x. And then we give this, we get this model. How can we get this model? Because this is the probability. So that we have this, the summation of all this. Let me just make a box here. So this is more like a probability. We have n minus 1 equations plus this one equation, which is, let me put an arrow here, this one equation. So we total have m equations. So what we actually get here is the thing that I have. Let me see, the summation of all these equal to 1. Why? Because this P is a probability distribution. So of course, by definition, a probability distribution is the summation of the whole space equal to 1. And hence, we can just do very simple mathematics because what everything can be expressed by this probability y equal to m given x equal to x. Y just give, have exponential each side, and then put this one here, put this one here. You know what I mean? And then so no, you don't need to put this one here. Let's say probability y equal to 2 equal given x equal to what? Equal to exponential of this part times probability y equal to m given x equal to x. So it's actually very simple, and the summation of everything equal to 1, and hence you can immediately get y equal to m given x equal to this. And then just plug in each j, let's say y equal to j, so you get this, So this is extremely simple. Okay, now this is the first step. I have the probability model. But did you see that I have and still have a big issue here? Is that I don't have the y, because I mean label y. So here I've already get, oh, betas, everything's good. I use this idea, but hey, here's a classification problem. So for a classification problem, you will be given an x, and together with a label y. It's a supervised learning, right? So okay, where's my y? In order to involve y in our model, I created like this way. I naturally apply the idea of multi-nullity distribution. So for multi-nullity distribution, it's just a let me see where it is. Here we go. It's just a the extension of Bernoulli distribution, in which here I have let's say m cases, n outcomes. There are gonna be only one of them, 1/n is successful, is success, or others would be kind of like yeah, sorry, I shall not say success here because we have m outcomes. Only one of them would occur, I should say, yes, and the other n-1 will not occur. So I model it in this way, which is the probability of pj times exponential yj. This yj is a binary 0 or 1. And the summation of all these yj's, j from 1 to m equal to 1, indicating that only one gonna occur. Exactly one, no, exactly one gonna occur. So what you're gonna have here is, it looks like I have p1 p1 power j exponential j1 sorry, p1 exponential y1, p2 exponential y2, blah blah till m exponential ym. Looks like I have m multiplication of m items, right? No worry, all others gonna be 1. Why? Because there's gonna be only one yj equal to 1, and hence all others gonna vanish. Why? Because x to the power of 0 is 1, right? Only one thing which really occurs finally gonna really have the pj. So exactly the same idea here. I have y follows multi-Nolly distribution of this one. So although I have so many p1, p2, blah blah until pm, which is corresponding to this, m of them, but actually only exactly one of them gonna occur. So here we go. And as we mentioned, this part, Zoom gave me a line. Okay, here we go. This part is corresponding to what? It's corresponding to this one. Which one? Here, this one, which is y equal to m. Why? Because everything depend on m, so that we just move this one out, So you can see here, it's not a j equal to 1 from 1 to m anymore. It's j from 1 to m minus 1. Why? Because when j equal to m, the PMF is this. It's different, from this form, and hence I move this one out. And also for all these, for j equal to 1 to m minus 1, it is this form. Okay, so that's the case. And I means the ith label or the ith data. Here we totally have n observation. Again, I'd better just write it down, just make sure it's clear. So I equal to 1 dot 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 n, and j equal to j equal to 1 dot 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 m. Okay, I means the number of data or observation. It means the number of features. Okay, so this is the same. And then so now I already have the y label. I have the something to be fit, which are the j, the betas, the beta j0, and also it's too big. Let me see, how can I make it smaller? Here we go. Okay, we have this, and we also have this. These betas are all decision variables that I try to fit. Okay, but how will you fit? What's your rule to fit, right? So the rule is the maximum likelihood estimation, MLE. So again, MLE, the philosophy of MLE, right, is what we believe that the samples we observed can be representative. The meaning of can be representative means that I try to maximize the likelihood of the thing that I observed, the training, the data that I try to observe. So this is the basic meaning of my maximum likelihood. And hence, so we can discuss two cases. Case number one is discrete. So this is directly the PMF, which is probability mass function, which is directly probability, which is very simple. Case number two is it's continuously distributed, which is a probability density function, PDF. PDF is not a probability, but still the multiplication of PDF can express the likelihood. The true probability, what, is PDF times dx, right? A small, very small delta of x movement. But here, to make my life easier, we just make a PDF, the density function multiplication. And then we want to make this thing the maximum. So this is the meaning of maximum likelihood. Or you can just go to lecture 3. Let me see. Here, I believe I've shared everything. I believe, yeah, this is lecture 3. So here has a very, very clear kind of definition of the MLE, in case you are not familiar with MLE. And then the thing in our case is that we have exponential. So we don't like exponential. What shall we do? Log likelihood. So because log function is an increasing function, I assume everybody knows the log function looks like this way. So sorry, it should be like this way, it's yeah, it's monotonely increasing, and hence, the solution of log likelihood is the same as of the solution of directly the likelihood, because we're trying to maximize the L theta, where theta here is the decision variable. Okay, now we can go back here. Sorry. I can go back here. So after some mathematical operations, I believe I show the steps here. Yeah, here we go. So after the log likelihood, but here are just very basic. You just merge, similar items and then do those kind of elementary school things. And then you finally can get the thing. But you do need to apply one assumption, which is one truth, actually, not assumption, which is the summation of all this yj, summation on the j equal to 1. Why? Because as we mentioned, there only one thing gonna occur, one feature gonna really occur. So that's the thing, and then you can get this log likelihood. So now I get the now I get the log likelihood here. So I need to choose the beta 0 and the beta such that this log likelihood function can be maximized. And then how to solve it? Well, this is not an easy thing to solve. I mean, it's gonna be, I don't know how many hours to explain the algorithms, but here the good thing is that in scikit-learn we do have numerical solvers already building. So I assume we know how to solve this, and hence our whole task is done, which is I get the beta 0 and the beta. And then once I get beta 0 and the beta, what shall we do? Simple, right? I just plug in all these things. And then for test data, I plug in the data. Then I'm going to observe what the data looks like. And then I will get for each label, I will calculate it and get the label with the maximum log likelihood, or with the maximum likelihood. And I'm going to classify the test data to that label. So that's the thing. Let me see here. Yeah, that's the thing. That's everything about the logistic regression. Okay, one thing I do want to mention, which is the relationship between logistic regression and Gaussian naive Bayes. Recall that here we discussed 3 cases in the naive Bayes. So for the naive Bayes, first of all, I need to get to the classifier calculation, and then by the naive Bayes assumption, which is all P features are mutually independent. So I can get rid of all these conditions and make it so simple like this way. And then we discuss, so we have finalized this one. For the purple part, simple. For the green part, we discuss for 3 cases. Remember it. The first one is the Gaussian naive Bayes, in which all the features are continuous and the domains are, and then we do this blah 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 the thing. Okay, so actually we can prove that if there are only 2 classes, all features are independent and all features are continuous features. So this is actually, to make sure that it satisfies the naive Bayes assumption. And then also here, independent of label Y. That's very important. Otherwise, in the proof, something's going to be wrong. So we can actually use the betas to express all these sigmas and mu's, and hence I can easily say that they're actually equivalent. Give me 1 second. I just realized it. I uploaded it to the server, but I forgot to. I forgot to update this one. So what I mean in this, so let's just regression. Sorry about it. Maybe I can just download and cover it. Let me see. I forgot to cover it. Download. Okay. So what I mean is here, there should be a link. Yeah, sure. There should be a link here. We can just use this one. Sorry about it. Let me just close this one. And then let me just make this thing. Place. Okay, let me reopen it. So it's here. So I believe, let me see, I believe it was the last part, logistic regression. Yeah, there's an expression here. Here we go. So this part is the proof. How do you make it? So basically, you just do some simple mathematics. I hope you're okay with exponential versus log, and organize the items so you can actually express in this way. Logistic equal to this and beta equal to this. You know what I mean? So hence, I already find an expression between mu and between mu sigma and the betas, and hence, of course, I can claim they're equivalent. So this is the thing. Okay, next, let me show two examples of the logistic regression. So let me first, Anaconda. I do need to have some cheatings for the parameters. Lecture 9. Regression. Huh? Wait, what happened? Yeah, nothing wrong. So why it stops me? Maybe, let me see. Okay. It doesn't allow me to use column. Okay, so here, first of all, I can just import all those things. And then from scikit-learn dot linear model, linear model import logistic regression. Okay, now I need to generate the Gaussian distributed data, training data, let's say. So x1 equal to np dot random dot multivariate normal, and then I need to have my cheating sheet. 10, 10, 25, 6, 6, 6. Wait, 6, 25, 50. Okay, the parameters here are negative 10, 10, 28, 8, 25, here's 60. I need to pay attention to here, yeah, because otherwise it's very easy to be wrong. 55, 0, negative 12, 21, 1, 49, 55. Okay. And then I can just do simple things. X equal to np dot concatenate x1, x2, x3, x is equal to 1, y equal to np dot concatenate y1, y2, y3, x is equal to 1. Okay, now I can train. What's wrong here? Size 0. Sorry, it should be x is equal to 0 because I'm gonna concatenate based on the rows, not the columns. And then what I'm gonna do is that I'm gonna train the model equal to a logistic. So here you can actually use a solver equal to whatever. But here in this simple example, let me just make everything default. And then model.fit xy. And then here I believe I print the training accuracy. Yeah, here let me print the training accuracy here. Print the training accuracy is model.score. So what's the meaning of training accuracy? That simply means I suppose I put the training data into kind of like using the training data to test, or you can kind of we want to see the test. We want to see the quality of the training data, the training procedure, the training accuracy of the training data itself. So this is the training accuracy. So here the training accuracy is 98.2. This is actually pretty simple, pretty good. Now let's have a look. I mean, probably people want to say, I want to visualize the data. Let's have a look at this data and let's have a look how the prediction gonna be. So let's say plt dot py plot dot plot x1 0 x1 1, and then let's say R label equal to training data plus 1 plus 2 plus 3. Okay, 2 3 2 3 3 2, and then oops, plt dot legend plt dot show. Let's have a look at the data. So it looks kind of like this way. And then as we mentioned, we want to kind of like really, first of all, we need to make a test data. And the second thing is I want to plot the decision regions, right? Okay, so here clearly, that's the reason why I need my cheating sheet for these parameters, because otherwise, if it's too far from from the lecture, the numbers, the result would be looking very, very different. So, and here you can see, indeed, here is kind of like a misclassification, see it? And the difficult region, where the difficult region, let me use another color, let's say orange color, is around, around here in the middle. Because in the middle is kind of like, it's really, really hard to say which part is going to be best. So let's say, let me ask you, what about this one? This is probably a misclassification, but how about here? It's really, really hard to say, right? That's the reason why we would like to plot the decision region, which makes it more clear. But before it, I can actually set up a test data. I believe in my slide that set up something here. Here, give me 1 second. Let me see. 6, 5. Okay, so here, have a look at here. 6 around here. 5 around here. In other words, I tried I tried to set up a troublesome test data here. Why troublesome? Because it's close to the boundary. You know what I mean? It's not like for example here. It's okay. Let me just make it. Okay. One very important thing is that in PyCharm, sorry, not PyCharm, what's it called? Scikit-learn library, it require the test to be like this way. Say, suppose I have, let me make one data to be here. Let's say 1510, let's say. And you say, hey, 1510, why do I need a 5D, five-dimensional data, right? Sorry, two-dimensional data. The reason is because another 6 5, right? In my yeah. The reason is because in order to let us test, simultaneously test multiple test data, and it requires you to make it to 2D. Even if say you have only one test data, it still must be in a 2D. Okay, so here we go. So then let me just make one here, make my life easier. And then I need to predict it, right? Why predict test predict equal to model.predict, and then X test. Okay. Now I predict this test data, and then I need to plot everything, right? And why don't I directly plot the what? Plot. Let me first plot this one first. Plt dot plot X test. Let me then I have to make a 0 0. 0 0 X test 0 1. I regret to remove it anyway. And then how will I make it? I can make it a dark black X, I believe. Where's my data here? Where's my I cannot find it. Oh, here. Black is marker size equal to 10. Okay. KX marker size equal to 10. And then I can have a label, which is, let's say, test data. Okay, now after it, I make it what? I will need to generate a mesh grid, right? So use the thing that we do before, linear space. Link space, sorry, link space. Then I'm gonna have X, I'm gonna have, let me see, X 0 dot mean. Let me see how much I left the space here. 10, okay. And the number is 200 X dot max plus 10, 200. One, and this is gonna be X2. Okay. Mesh grid. Okay, now I have this one. What else do I need? I can directly make, right? I need DR color. Decision region color again, equal to listed color. And then I believe it's light coral, light green. And the third color is light blue, or maybe let me see, what is my I cannot find it again. Light blue, yes. Light blue. Okay, now of the colors, what should I do? P mesh grid, right? Before wait, I need the prediction as well. Prediction equal to model dot predict np np dot array dot p here, and then rebels x1 dot rebel, make it to be, make it a flatten it to be a vector. Otherwise, the dimension is gonna be wrong, and then I can have give me a second, one predict here, model prediction here, so I can have plt dot p color match x1, x2. Let's say name it a dr predict here, no y predict, dr predict. Let me see, dot reshape I need x1 dot shape, and then C map equals to dr color. And then yeah, actually, let me see. Okay, here we go. And then you can indeed see the test data here. The test data here is, to be honest, because I just want to make it, kind of like easier. I can definitely make it to be wait, why there's nothing? I can print here. Let me print the test data belongs to class model. No, I already predicted it. I just need to have y test predict. Okay. The belongs where let me make it more beautiful. Sorry about it. First, I don't need this one. I'll make it to be this. So at what directly show class 1 instead of class, what is wrong? The keyboard is so small. Okay, here we go. So class where does belong to class 1. Oh, we can make it to be as type integer. I mean, here, let me see. So here we go. So dot as type integer means I enforce it to be an integer. So there's no 1.0. Otherwise, it's going to be kind of float. Okay, now indeed it's here. Of course, you may say, how about why you test it here? Because this data is very easy, right? Why don't you test it here? Like in the slides, I'll make it to be 6.5. Yeah, I can definitely make it. Let's say 6.5. And then give me 1 second. So this one, the test belong to class 6. This and say the second one. That's the one and this. So so you will see kind of one and maybe another one. Yes. And then here, let me see, for the plot, I can write let me see. Okay, and one. So 6.5 is around here. Wait a minute, 6.5. Wait, why it looks so let me have a look here. Let me see here as 6.5. Why 6.5 here? 6.5 should be around here, right? Let me see. Where's my code? Here. Yeah. Whoa. Let me see. Let's see. Colon dot 0. Yeah, or maybe I can just make it to, let me see whether I can make it like this way. But the thing is, this is not array. This will probably be wrong because this is not array. Although this is not a big problem, really. Yeah, this is not array, so I cannot make it like this way. So, or maybe I can make, let me do like this way. Empty dot a array. I don't know. Oh, sorry. I don't know whether this can help. Yeah, here we go. So it's more like this way. So here is 6.5. The other is what's the number? 15.10. So 6.5 is indeed more dangerous, but the decision region is kind of like this one. Again, why every time the number is going to be different? Why? Simply because I randomly generate the data. And hence it's all the time you run it, the data going to be different. Decision region would be relatively closer. No, I cannot make this conclusion, but yeah, the decision region and the test data will be different. So here we go, and the training accuracy this time is 99.4. The class belong to this is 1 and 1. Of course, you can make it like this one. Let's say you make it negative 50, 10. So it should be the first number should be belong to this class 2, and then the second one should be class 1. Let's run it. You see, class 2 and 1. Here we go. Okay, so this shows how to run the decision, how to run the logistic regression here. And then let's see the next one. I believe the next example is a credit card. Yeah. So here's a real application, which is applications of logistic regression, such as super simple regression model, logistic regression model, but it's widely commonly used in credit card approval. And I don't know whether you've seen like 20 years ago, let's say 10 years ago, I believe at that time, I should say many actually, some of them, let's say some of those kind of credit cards still need to wait for 3 business days for them to make a decision. But nowadays, for 20 years ago, almost all banks, you say, hey, have a credit card application, and it will tell you, hey, you need to wait for 3 days, sometimes even 1 week, around 2000 to wait for it, because at that time, those kind of machine learning concept, was not that common. But now, I don't believe you can find any bank gonna say, hey, wait for like 3 business days or 1 week. No, almost all the thing gonna be finished within 30 seconds, or let's say 1 minute. And to be honest, 30 seconds, 1 minute, mostly not because of they're really computing like the model, fitting the models. No way. Simply because some system wide or something like they need to make sure that the data not gonna be stolen, those kind of things, or the server, the internet speed. The time for them to make a decision actually, based on your data, maybe just 1 second, even less than 1 second. But anyway, here let's show a super simple example to see how it works. So we consider let me show the data here. Value base, I don't need it. I can have this one. Okay. Here we go. Okay, so this is the data. So this data does have, let me make it a bit, I know it's a CSV format, but just let me just make it, better for us to read it. Okay, let me just make this one here. Okay, now let's make it smaller, and then okay, here we go. So now we can see the things here. Okay. So indeed, so first column is decision, approval or denial. So 1 is approval, 0 is denial, and we have 1, 2, 3, 4, 5, 6, 7. 7 features to consider, which is age, married or not, education level. So age is just age between 18 and 70. I know nowadays some banks even allows children like 16-year-old can apply for credit cards. But usually it was like at least 18 years old. Even if you say I'm a 16-year-old, I have a job, no, still, there's a kind of like age. 70 is for many banks, it's the kind of like the upper limit of age for you to apply for a new credit card. Married is yes or no. Yes means one, no means zero. Education, we consider five levels. Well, at three, four, five two sorry, here's the typos. Five is PhD, four is master, three is bachelor's degree. Here should be two and one. Sorry, here are two typos. Two is high school, one is lower than high school. And then basically, again, it's on average, okay? I mean it's just a statistical data on average. The higher education, the better credit on average, again, you will be. Similarly for married or not, usually married person gonna have a higher chance or let's say lower chance to default. Age usually higher age, the older means you have a smaller chance to default. Years employed, which means how many years have you been employed? I believe here years employed means full-time employed. Instead, however, it's somewhat unfair because in some cases say I just have several part-time jobs. Why I should be full-time employed? But here, again, here's just an example. It doesn't mean your current job. It means, the total in your life, how many years. And then usually the higher number of years you have been working, the lower chance you will default. Prior default, this is a very, very critical number. However, here I assume I don't know it. I want the model find it by itself, which is number of defaults in last year. So clearly, if the person have a lot of defaults in the last year, no matter how other things are, probably the person gonna be directly rejected. So this should actually be a not dominating factor, but let's see how the model will find it. Income is the annual income of last year. Usually the higher income you have, the lower chance you're gonna default. Finally, credit score. Credit score is something for like a general, reference. So these are the things. So let's just randomly find some samples here. Let's say the first person. Okay, age is 22, married, not married. Education is bachelor's degree, years employed, one, probably a new, a student who just graduated from the college. Prior default 0, income is 47,000, credit score 680. Well, the bank still gives the approval. Let's find a typical, denial. This one, age is 20, pretty young, not married. Education's high school. Sorry, this should be 2 again. Sorry about this. 2 is high school. Never employed, never default. Income's 14,000. Credit score is less than 600. Never default, probably because the person has never got a credit card. So of course he or she even didn't have a chance to default. And then unfortunately denial. And then let's find another person. Let's say this person, 55 years old, married, education is master's degree, years employed, 28 years, prior default 1, income 72,000, credit score is 763. I know some of you may have a question that, hey, how come the person have a prior default, but the credit score is still 763? It's possible. Indeed, it's practically possible because nowadays many banks has a program called something like what is called? Like default free or default pardon, whatever the program. Basically, it allows you to have most bank, I believe the number is 1. It allows you to have one time of default in the whole year. So if it's one time in the system, although it's 1, it will be considered to be 0. The reason because just in case, some cases, some people, the money chain, the cash flow may have problem, or sometimes I just have a trouble, say I didn't set up automatic payment, and I didn't check my email, so I forgot it. It's possible. It's kind of like possible, and hence in many cases, one, especially with this age, this income, one could be just kind of like excused, and hence it's make it to be 0, and that's the reason why. And some other cases like the person similarly, you can see although 0 default, income is just the average, and then sorry, I'm saying this person, incomes below the average, default 0, years employees also, this is okay, education's average, married, no, this is. So we have this number of, let's say 68 training data. And from this, I want to first of all train the model. What's the meaning of training the model? Which means I want to find these betas. And then using the model, I want to tell the next one is where's my number? Is this test data? The test data is the person going to be 40 years old, married, education 3 means bachelor's degree, years employed, 16 years employed, pride default is 0, income is 50,000, credit scores are below, credit scores are only 600. So I'm going to ask you, hey, whether the person going to be approved or denied. So that's the thing. Okay, now let's see how can we code it. Okay, let me just copy and paste. Okay, I need this, but I don't need to plot anything. So I don't need a pie plot. I don't need the color. I need the pandas. Uh, okay, now I need to find what I need to find the path of my. By the way, some of you may question why every time you write the path and make it R. So this R parameter. So this R parameter means the raw path. So this is more general. And if you run the Anaconda, you may have seen you have the Jupyter Lab Cloud. Here. Cloud notebooks. So here, because I have some personal things inside, so I do not use the cloud. But if you have a account in Anaconda, I believe free version gives you how many? 10 gigabytes or 100 gigabytes something, so you can really use a cloud, and then you can just run everything in one place, and then you can just upload those kind of this kind of data, so that as long as it's under the name of Anaconda or under your root, you don't have to write like this way. You can just simply make, let's say abc.csv, done. You know what I mean? You don't have to write the whole directory. So that's the thing. The reason is because I hate to put everything just under one folder. Let's say, let me see, where is my Anaconda? I believe users. This is mine, and then Python. No, Jupyter. No, let me see. Dot Anaconda, and no, I forgot Anaconda. I forgot where is the place. Let me find it. Maybe favorite. No. There's a place here. There's a place here that you can, let me see. Yeah. Here, sorry about this one is right, this one. So if you go to the root of this one, so this folder is exactly this folder, which is just the user, you put your username, and you can see that's our, these are all those kind of .ipynb, a Python notebook, Jupyter notebook. These are all the things here. So if you want, you can just copy and paste. Where's my data? Lecture 9. You can just copy and paste. Let's say you can put this on here. And then you can directly run it. You know what I mean? Say we can just try it, so that this time I don't have to run the R, parameter anymore. But it's just more general, just in case, so I can do it like this way. And you can see I run, there's no error. I can read it. Why? Because I do have the CSV document, which is right under the directory, which is right here. You can see here. However, in most cases, you don't want to, it will be a big kind of like messy organization. If you have everything all together here, you know what I mean? You may want to have something kind of like, for example, you have a folder or something. And in most cases, I know people don't want to put the things right here in the C, drive and write in your username. And that's the reason why in most cases I show you this method, because in my personal view, just my personal view, this is gonna be more robust or safer. Okay, so I can have this path equal to this one, and then I can have data equal to pd dot read csv, csv, and then path, and then I get the x equal to data dot job, data dot columns, Uh, the first or the last one? The first one, okay. Is equal to 1, and then y equal to beta dot columns 0. Okay, so now I have x and y's. Now I'm to train model equal to log. Logistic. Here, I believe I use a solver. Let me see. Yeah, here we go. So this is a widely used solver here. I'm not sure whether it's default or not. You can just check the document of LGR logistic regression. Here I just want to show how to apply different options of solver. This solver is pretty powerful, so that I specifically mentioned this solver here on purpose. So the solver is gonna be a linear, and then I can just train my model dot fit x y. And now I'm gonna do what I can print hash item. I set the training accuracy. The training accuracy is model.score xy. Okay, let's check it. Oh, great. Labeling your instead. Yeah. Sorry, I need the keyword solver. Okay, so I need this again. np dot options dot set options precision equal to 3. So I don't want to. Wait, is it np dot? Or maybe no, this one. Let me see. What did I do here? Uh, wait. How can np set options? Give me 1 second. Sorry about it. I believe. Anyway, let me. Here I actually don't need. I don't need this. I can use this. Okay, so the training accuracy is 0.926. Not too good, not too bad. And then we can do what we can do the test. So the test number is 41,316,056. Okay. So the x test equal to 41. I remember bachelors, and then what? Forgot again. 16. Okay. 16, 0, 50, 600. So basically the person, 4-year-old married, bachelor's degree, 16 years of employment, 0 default, income 50,000. The bad thing here, because if the credit score is higher for sure, but the credit card is pretty low. So I want to ask, hey, whether the person gonna be, approved or denied. Okay, now y predict equal to model dot predict x test. Again, let me put S type. Otherwise, it will make 1 dot or 0 dot, something like this again. Okay, now I can just print the decision of the test person is, let's say, approval as 1, denial is 0. Okay, so finally the person gonna be approved. I can of course make it like this way. Okay, yeah, the person's approved. So that's how we can use this one. And in real application, of course, banks have, I don't know how many data, hundreds of thousands or even millions of data. So I believe they do have enough, training data. And then for a new applicant, what's going to be? So that's how. And indeed, the logistic regression is widely used in credit card approval, automatic decision even today. So that's everything about logistic regression. Any questions? No. Okay. So the next topic would be, let me save the one. The next topic will be support vector machine. And as you may have realized that before I mentioned the discriminant analysis as well, like LDA, linear, or QDA, quadratic. Due to I calculated our classes and I realized that I may not have enough time to introduce LDA and QDA. So LDA and QDA on average, in this class later, because here we will show the what comparison of the solvers here. Oh, sorry, of the classifiers here. LDA in general, I'm talking about this one. So LDA in general, the results is not as good as these two, and LDA is not in general, again, not widely as widely used as, for example, things like SVM, LGR, or naive Bayes or KNN. And hence, in this class, this time, I actually, kicked out the topic of discriminant analysis, and hence I directly move lecture 10 to be the support vector machine. So this is the thing. Let me go to support vector machine here. So support vector machine is an idea that I try to use hyperplanes, which is called hyperplane, separating hyperplane to separate the two classes. So this is a very big idea. Let's see how can we apply it. So given the data here, these green triangles are class 1, these blue circles are class 2. So I'm going to ask you, can you give me a hyperplane to separate them? Or let's say here I have L1, L2, L3, L4. Which one would you choose? I believe most people are going to say I would choose L2. Why? Because kind of like L2 is like in the middle, right? And also it makes like the two groups like kind of like in the middle of the direction of the two groups. In the direction is which direction? In the direction that the two groups are the furthest. So for example, suppose you see, let me zoom, give me a double. Okay, so if you have a look at the red one, let me show a red color. Okay, the distance is like this way. And then if you, for example, you show the black one, the distance is gonna be something like, suppose you see, it's gonna be something like this one, right? Sorry. It's gonna be something like this one. And you can see this black double arrow is shorter than this red arrow. So, that's very, very intuitive, like explanations that I want to have like a hyperplane here called the separating hyperplane, which can actually distinguish the data of the two classes the most. Okay, then I will immediately ask you, what do you mean by the most? How do you define, like, distinguish the data in the classes the most? What does most mean? Okay, in other words, we need need a metric. So our metric is in this way. So in addition to the separating hyperplane, I will have two margins as well. The two margin lines are here. So we want to choose a separating hyperplane such that the distance between the two classes among the normal direction of the separating hyperplane is maxed. So here we're gonna need the direction, the normal direction, the same thing as here, sorry, clear, okay. The same thing as what we did here. Remember, we plot those kind of lines. I need this kind of the directions of the normal direction and the separating hyperplane. And be careful that the margins we plot here must be parallel to the separating hyperplane. Okay, that's the reason why just now, say here, suppose I have two black color. Give me a black color. Okay. Suppose I have two, I consider black color. It will be something like this. Remember what I mean? And hence, remember, we plot the double arrow like this one. So this is distance. By comparison, if I choose the red color, I can plot the margins to be something like this. Again, they must, sorry, it's not parallel. It's just difficult to plot something like the real parallel things by hand. And here it will be something like this way. And then my red double arrow will be what will be in this. And you can see, so here I can have set up my most. That means this distance. I want this distance to be as big as possible. And hence I can say that I will distinguish the data in the two classes the most. Okay, so this is the basic meaning. Okay, now we have the separating hyperplane of the margins. So the margins, the definition is, first of all, I will let's say first of all, I will be parallel to my separating hyperplane. And the second thing is what? The second thing is here I'm gonna define the number, define the 2 points. The 2 points gonna call the support vectors here because they're right on the margin. But be careful that here is just a fundamental idea, and later you will see this is called hard SVM, support vector machine model. Later we'll have the soft support vector machine model, which is going to be kind of different from this definition. It will be changed. Here we're only introducing the hard support vector machine model. So the support vector is going to be on the margins here, and then by the distance means the distance of the 2 points with respect to this direction. So that's the thing. Okay, now we can have this separating hyperplane here. Margin 1 is here, margin 2 is here, and then our separating hyperplane without loss of generality is going to be always in the middle between the two margin lines, and hence I can make both distances to be r. Be careful here, r is the distance. Okay, it's not a vector, it's just a distance. Okay, now I have defined the separating hyperplane, the margin 1 and margin 2 here. For convenience, we only show the the thing for two classes. Later we'll introduce two models for modeling if we have more than two classes. And the whole system here, which means the idea separating hyperplane, the margins and support vectors here are called support vector machine, the whole system, SVM. Okay, so now let's see. But here again, it's kind of like a general idea. I just want to maximize the 2R or maximize the R here. The problem is, how can you define R? I need a mathematical definition, right? Well, in the plan, we can always write, for a linear function, especially if it's 2D, I can always write in this way. I can say, for example, I can say, let's say y equal to, give me a second, Zoom, give me a writing here. I can always, y equal to, let's say, wx plus b, right? So this is a function. So of course, for the separating hyperplane, I can write in, for example, I can write it in this way. W0 plus B0. I can write it in this way. And for the two, I don't allow me to copy and paste. Interesting. Okay. For the two separating hyperplane, sorry, for the two margins, I can write, for example, W0 X. Be careful, they are still W0, okay? Why? Because they are parallel plus, let's say, B1. And the other one can be, y equal to WB0 plus B2. You can write something like this one. And in the higher dimensional hyperplane, we can always write in the higher dimensional, we can write what? We can always write in WTX plus B. Be careful, B is always a scalar. And then WT here is a vector. It doesn't have to be 2D. It can be 10D. It don't, whatever dimensional, it doesn't matter. Because WTX is always a scalar plus scalar. So in other words, what I'm saying is here. So I can always define, I can always define this separating hyperplane, the equation, to be WTX plus B equal to 0. People may say, why it's plus B equal to 0? Why not, let's say, equal to 1, equal to 2? The same thing, because I can always, no matter what number you have, I can always move it to absorb this number to be B and make it to be 0. So without a loss of generality, I can always define it to be WTX plus B equal to 0. Okay, and then this is a little tricky here. I can always define the margin to be WTX plus B equal to -1 and the WTX plus B equal to 1. I know this point, if it's your first time to see support a vector machine, you may be very confused. Why do you define this way? So why you enforce it to be -1? What if what if the truth is that it's -2? This is, let's say +2 or whatever thing. How can we do? The truth is because no matter what number this is, you can always rewrite it to be this form. So I believe here I showed an example. For example, suppose, okay, suppose the truth is WT0TX plus B equal to 1. Excuse me, sorry. And then the other one equal to 2. These are the equations of my two margins. What can we do? What we can always do is like this way. We can always convert it to be here and here, so that I can always, give me 1 second. I can yeah, I can always make this one. Let me see how I can convert to be this way, which is 2WT0x plus this one equal to -1, and 2WT0 2x plus this one equal to 1. And thus, I just need to set up W equal to 2W0, B equal to this one. So I can write the whole thing again to be what? To be W2x plus B equal to -1 and a positive 1. Let me show mathematically how can I do it. I need to open the Microsoft Word. Okay, so what I mean is this. Suppose I have, okay, now suppose I have this. I have, let's say, W0T, oh, 0T, what's wrong with that? W0T x plus beta 0 equal to 1. Be careful, here are vectors. The thing I have is, oh my God, it's great. Let me just write in this way. Sorry about it. Let me see how can I believe I can write it. Oh, okay, here we go. Here we go. Make my life easier. Huh? Okay, and the other one is what? Sorry about it. Okay, now I can let me make it a bit bigger. Let's say 15. Let me in the center. Okay, now I hope it's more clear. So now I have what? 1 and a 2, right? Suppose I have this, okay? Instead of and what I want to show you that whatever number you have, I can always convert it to this number. So what I'm gonna do is here. So in order to make this one to be 1, what can we do? Let me see. Let me see what can we do here. Let me copy and paste. We can we can ah, well, we can equivalently write two equations to following. So I want this one to be -1. Give me 1 second. Give me 1 second. Give me 1 second. What can I do here? Basically, I wanna, let's say, okay, let me do this. I time K, okay, I can make a K here. I time K from both sides. K equal to, let's say, K minus 3K. Give me 1 second. I want a -1 here, right? So I minus 3. Wait, KB minus 3 equal to 0. And then let's say, give me 1 second. Here is, oh, wait. Let me do like this one. The first one is times K, and minus K, sorry about minus K equal to 0. Now I want to make it to be 1. So I'm -1 again, -1. Okay, the second thing is similar. Times the K, because I want to get this K. Plus 2B minus 2k equal to 0, but I want them to be 1, so I'll make it to be plus 1. Okay, these two things are the same. So how can I solve the equations here? I will have, let me see, if that's the case, can I have, let me see. And by this one, I can naturally get k equal to 2 here. And then we just substitute it. We will get what? We'll get here's 2, 2, and then 2b0, k equal to 2. So 2 minus 1 is 3. And then k equal to 2, 2, 4, 4 plus 1, yeah, it's also 3. Here we go. And you see, I can just put a parenthesis here. That's how I get the numbers. Okay, in other words, I can always define by defining by defining, let's say w equals to 2 w0 vectors and b equal to 2b0 minus 3, we have these two equations. Make it to be -1, +1. This I don't have the b. This is wt here. And the this is the -1, the first. So here we go. That's how we make it. In other words, it doesn't matter, what this parameter is. I can always use a trick to write it to be this form, which are, wtx plus b equal to -1 and the wtx plus b equal to +1. You know what I mean? So here we go. And of course, we can have the thing just in the middle, which is very simple because here, -1, +1, which is the middle one. Middle one, of course, is equal to 0. So that's our system. Then I already defined the w and the b. Then I want to have the R. Why? Because our purpose, the idea of SVM is to maximize the true R, right? Okay, so how can I express R with respect to W and B? So we can use this trick. So let me, so here, suppose I have a support vector X on the margin here. So I just make the projection of this X onto my separating hyperplane. I call it X projection, XP, let's call it. So this is XP. Well, we know that the distance from X and XP projection is R, but how can we express it? So we can actually have this. Actually, I already wrote it here. Let me just use this one. Color. Okay, let me use this. Okay. So I can have what? Suppose this is a vector. Let me call it, suppose this is called vector V, let's say. Okay, so 1 second, let me make it bigger. Okay, so what I have here is I have XP projection, PRJ. X projection means here, okay, because here I can type the latex equal to what? Equals to V plus, I should say this, X equal to X projection plus V. Maybe I can, these are all these are all vectors. I cannot, oh no, zoom down to let me write the bold. I'm sorry about it. So I have this, right? And the V is right here. This one is vector V. This red one, what what I mean is this red one, the one I just plotted. So clearly this is X projection. So of course X equal to X projection plus V. All these X projection and V are vectors, okay, right? Okay, now X is still X projection is still X projection. How can we express V? Well, I know the length of V is R. I know the direction of V is the normal direction, right? Okay, so I already know this separating hyperplane, the equation is WTX plus B. How can I write the normal projection, the normal direction, unit normal direction? Simple, it's just W over the norm of W. I assume everybody knows this one. Let me just use an empty page here. Let me just, you know. So let's consider the thing that we're familiar the most. So let's consider 2D. In the 2D, so suppose I have let me plot like okay. Let me just use black color to plot. Zoom, the plotting system is really complicated. So suppose, this is X, Y, right? Okay, now let me create a line which is thinner. Let's say suppose this is a line. So suppose the equation of this line is Y equal to AX plus B. Then let me ask you, what does this mean? This simply means the tangent of this angle is X, right? Then let me ask you, how about the norm? How about this direction? Give me an arrow. How about this direction? This direction is what? Wait, how can I have a okay, okay, just let me directly handwriting. It's so complicated. Just okay. So this direction, the tangent is gonna be what? Negative 1 over A, right? And then what's gonna happen is that what if I ask you the gradient of this one, or let's say the unit how to say the unit direction, the unit norm direction of this one, what's gonna happen? So that you are gonna have what? You're gonna have actually I don't know how to make it. This gonna be like negative 1 over A divide by the norm of it, the norm of 1 over A. Be careful here. Let me see here as A is actually a vector. This is simply give me 1 second here. I get a bit confused here because here is, oh, I know why. Okay, I need you. Oh, can I? Okay, okay, here we go. I need to, how to, can I use this one, erase? Okay. So in order to write this one, I actually need this. So this one, the gradient gonna be A and then -1. And then this one gonna be -1 over A and -1. So in other words, if I want to make the gradient of that, it's gonna be this. It's gonna be, let me still write it, right? Writing is easier, although it's ugly. 1 over A square root of A square plus 1. So this is gonna be the unit direction of that one. So basically you have this A, but you need to kind of like how to say, you cannot make it to be the A itself. You need to make it, like this way. And then let me, sorry about it. Let me just erase it. The unit is gonna be in this one. A squared plus 1. And then this is also the same thing here, -1. A squared plus 1. And in this, you can guarantee that, first of all, this gradient is a unit gradient, meaning the length is 1. Why? Simply because of this numerator denominator item. The second thing is it is indeed this direction. You know what I mean? In other words, it's nothing but this direction divided by the length. So let's go back to this one. Isn't it similar? I already know my gradient here is W, and I ask you what is the unit norm direction. So the gradient should be W over W norm. Here again, I mean, without loss of generality, we use Euclidean norm, 2 norm. Okay, so here we go. And then I can express it, X equal to X projection plus this unit direction times length R. Okay, now we can multiply left multiply WT, both sides of the equation. WT and a plus a B, WTX plus B. Here WT X projection plus B. And then here's WT, W over 2 norm of W times R. But you know what? Have a look at the two equations. So you may ask me, why do you want to multiply WT? Left multiply WT and the plus B on both sides, because I want to take advantage of these three equations. Because I do know that WTX plus B on margin 1 is -1, on separating hyperplane 0, on margin 2 is 1. And hence you see here, what do we have here? WTX plus B is my X. But my X is what? Is on margin 2. And hence I know WTX plus B equal to 1. And hence this number becomes 1 here. Similarly, this this X projection. X projection is what? X projection is actually on my separating hyperplane. And by definition, I know X WTX projection plus B equal to 0. And hence this part becomes 0. And I only have this, the last part, which only includes W and R. And then I have this. Be careful that WTW is always equal to square of 2 norm. Why? Because what is 2 norm? Suppose I have 2 W's, you know, okay, let me write it by hand. Okay, so suppose I have 2. So let me use another color. I wish this part of Zoom can be improved. That's so difficult to write some formulas. W2 norm of square. So I don't need a square root equal to what? Suppose I have just 2D. Okay. There's no 2, sorry. Suppose I have only 2D, okay? Isn't it this equal to W1 square plus W2 square, right? Okay, then think about it. What is WTW? Isn't it also W1, W2, and then W1, W2? Isn't it also equal to this one? That's why WTW equal to the square of W2 norm. And then square W2 norm divide by W2 norm, which means what? Which means R equal to 1 over W2 norm. W norm, let me just call it a norm, which is easier. And hence I successfully expressed R with respect to W and B. Actually, B doesn't matter because B is actually just, you know, like a movement, like a shift here. But W doesn't matter because it's a scale or the tangent of your hyperplane here. So we have this. And again, what is the idea of our support vector motion or hard support vector motion here? I want to maximize these two distances. In other words, I want to maximize the R, right? And hence the original function should be maximized of this part. However, we will write it to be minimal of the inverse. So first of all, maximize of a number, let's say maximize R is equivalent to minimum of inverse of R, given that R is a positive number, right? The same thing. But why I want to write it to be minimum? Because minimum, this is going to be a quadratic function, which is easier. By comparison, maximum, you have variables in the denominator, which is more difficult. And again, you may ask me why you're writing a 2 here. Because maximum of 2x is equivalent to maximum of x. The 2 is because later we will get the derivative or the gradient here, so that this 2 and this square 2, you know, after derivative, they're going to cancel. That's why on purpose I'll keep the 2 or a half here. That's the reason why. And then how about constraints? You can now say, oh, okay, I want a minimum, you know, let's say W norm. So what's some solution? W equal to 0, done. Which is easiest way. No. You need to satisfy some conditions. The conditions are what? Conditions are, well, if all the number, all data in class 1, their label is -1, while if all labels in class 2, their label is +1. Now I understand the meaning. Remember when we just introduced the general concept of supervised learning? I said, well, for the supervised learning, the sets can be defined differently. I believe it's in Kenyon's neighbor. Let me open it. Let me see here. Yeah, here we go. I said, well, we can define to be 0, 1, 1, blah, blah, n minus 1, especially for m equal to 2, in which we have 2 classes. I can also define it to be -1, +1. Now you know why I want to define in -1, +1, because I can write a form like this way. Because here I define yi to be first class to be -1. If data I is in the first class, I define its label y yi equal to -1. If a data is in class 2, I define the label to be +1. And hence, I can immediately write the whole equation to be this way. You see what I mean? But comparison, if you make it to be 0 and 1, you cannot write it this way because 0 times any number becomes 0, and then you will have troubles. So think about it. This means if y is in class 2, meaning if data I is in class 2, meaning that yi equal to 1, I just have what wtxi plus b is greater than or equal to 1, which makes sense. Why? Because let me give me an orange color. Okay, because this line is already equal to 1. So on this direction, what is the equation? Should be wt plus b greater than 1, greater than or equal to 1, right? This means all data in this direction. Okay, similarly, what if my data I is in class 1, so that I have yi equal to -1. So -1 here, you times -1, you will have wtxi plus beta less than or equal to -1, right? You times -1, you need to change the direction of this inequality. So here, this line means what? This line means equal to -1. So how can I express to be this direction? Isn't it everything, the wtx plus beta plus b should be less than or equal to -1? So it's this equation again. You see what I mean? So if I define y to be -1 and a +1, the label like this way, I can write SVM super simple, just one equation in the constraint, one inequality in the constraint, like this one. No matter y equal to +1 or -1, you know, this inequality satisfies our constraint. In general, this is our SVM model for two classes. So here I wrote quotation original because later we will see this is actually a hard SVM, not a soft SVM. You will see the next 2 slides, I believe. Not just 3 slides. So that's the thing. Okay, then let's go back again. So the optimization objective function is to maximize this R. Because maximize R is more difficult to be solved, I minimize its inverse, which is minimize half of W norm, subject to all these training data are in this side. All training data in class 1 are in this side. So this is the constraint. Done. Then how to make a decision. So suppose I've already solved this model and I have my W star and a B star, meaning the optimal solution to this model. Now for target data, I just need to plug in. Very simple. I just plug in, here W star T X plus B star. So I just need to see whether it's greater than or equal to 0, greater than 0 or less than 0. If it's less than 0, by definition, it's going to be this direction. In other words, it will be what? Class 1. If it's this direction, sorry, if your fx if your fx is greater than 0, in other words, it should be in this direction. So it must be class 2. So that's how we do, okay? Again, the key here is that your decision variables are W and B because, based on my previous teaching, experience, I don't know why many students would consider X and Y to be decision variables. X, Y, and Y's are your training data. They're given. But W and B's are something you don't know. Okay, so this is a great idea looks like, right? But didn't you realize that here we have a fatal assumption when we introduce the whole story here? What is a fatal assumption? Which is, you see here, all the green points, all the green training data gonna be here. All the blue training data gonna be here. But in the real application, for example, we saw from I just closed it. Let's say logistic regression. The real life is never like this way. The real life is gonna be like this way. Say, for example, a red point is here. Blue point is here. So in this case, how can you make it? You cannot use this model anymore. Or for example, consider this one. Suppose this is your training data. We can see that I have a blue data here, and I have one green data here. Let me ask you, how can you formulate the SVM? This is no matter how you plot your line, you cannot make it such that all the training data in class 1 belong to one side, all the training data in class 2 belong to the other side. You know what I mean? Say, for example, if you cut your line like this way, no way. They're gonna still be misclassification. kind of data. Let's say this direction you see here are, class 1, and here even more training data class 2. In other words, the model that we just proposed, in which we have the assumption that all the training data, I can find a separating hyperplane such that all training data of one class is going to be on one side, and another group of training data going to be in the other side. This assumption is wrong. In most cases, I should say, this assumption does not work. Then how can we formulate it? Does it mean that I'm gonna fail? No, it doesn't mean. What does that mean? What it does mean is that the idea of this original, or we call it hard margin SVM, gonna fail. But we can modify it a little bit, make it to be the soft margin SVM as follows. So first of all, we still have the same notations, but this time we allow two things, two cases. Case number one is called, let's say, we allow the data. Let me just highlight it. Give me a color. What happened? Okay, lines. Give me a color. Let me use the orange. Let me use the red color. The case number one is the data to be inside the margin, but still in the correct side of the separating hyperplane. Examples are x2 and x4. What does it mean? So look at x2, for example. So x2 can see. So in our hard margin SVM, all the training data from class 1 should be in this side of my margin, right? While x2 is not. x2 is inside your margin, but it's still the correct classification. Why? Because it's still in the correct side of your separating hyperplane. Because remember our decision? Our decision is that if you plug in this target data x, if fx is less than 0, meaning that it's in the, give me an arrow, meaning that it's in this direction of your separating hyperplane, then it's going to be class 1, right? Now, if you go back to erase it, okay, if you go back to this case, so you check x2, see it? If you plug in x2 into this model, you will see what? You will see that x2 is still in this side of your separating hyperplane. In other words, if I'm going to ask you, hey, what is the class of x2 by the model? You will still say it's class 1 because it's in this direction, right? Okay. However, it is inside the margin instead of outside the margin. So outside the margin means this area, which is not, between the margin and the separating hyperplane. It's outside, which is an ideal case. It's not an ideal case, but I can still tolerate it. And the case number two is case number two that we can tolerate in this case, completely in the wrong side, which means it's a misclassification. For example, you look at a class 1 and class 3. So class 1 should be not class 1, x1. x1 should be in class 2 because this is the label given in the training data. But the truth is that in this model, it is in the other side of separating hyperplane. In other words, if I plug in x1 into your model, I will have fx1 less than 0. In other words, by my SVM model, I will predict this x1 to be in label 1, in class 1 instead of class 2. So this is called a misclassification. The same thing as x3. Where's my x3? x3 is here. This x3 is, actually it's across the separating hyperplane. In other words, it's going to be a wrong classification, misclassification. So in our soft margin SVM, I want to consider these two cases into our model. Question, how can I make it? How can I correspondingly revise the model to make it to be, to make these two cases to be included in the model? So what we're going to do is that we will create a new variable called CI for the ICE data. I will use the CI to count the penalty from data xi to the correct margin. So this is going to be, for example, from data x1 to correct margins here. This is CI1, CI2, CI3, CI4. So I want to apply the following rules. Rule number 1 is that if xi is in the correct side of the margin, not the separating hyperplane, okay, the margin, there's no penalty. In other words, this CI equal to 0. So for example, you can, see, let me directly plot. Okay, plot is easier. For example, let me use, let's say, orange color. Let me use the orange color. Let's say here, All these data, they are all correct. And also here, see, these data, they are in the correct side of your margin. And hence, I don't give you any penalties here. My KCIs are 0. And then case number 2 is corresponding to the first case here, that if xi is in the wrong side of the margin, but still in the correct side of the separating hyperplane, then I try to get your KCI to be between 0 and 1. In other words, let's say x2, you see it? x2 is in the, and also x4. Where's x4? x4 is here. Okay, so both of them, let's say x2, it is in the wrong side of your margin. The correct side should be here, but x2 is inside. However, in terms of separating hyperplane, it's still correct. In other words, this is still, although it's not that good, but it's still a correct classification training data. It won't be a wrong classification. So in this case, I want the penalty to be between 0 and 1. By the way, why it's between 0 and 1? Why don't I say that's between 0 and 10? It's simply because of my settings here, because I define this margin to be -1, define this margin to be +1, define this separating hyperplane to be 0. In other words, the distance, of here, I cannot say distance. I should say the distance, without considering this how to say this W gradient, it is, or I should say the offset. Let me use the term offset because the same for Python, or the levels. If you plot the contour, it's gonna be 1. This is 0, this is -1, this is +1. And hence, I would like to set up the C, a penalty, to be between 0 and 1 instead of between 0 and 10. That's the thing, to make it consistent. Other words, this C may dominate everything. And the case number 3 is that if X is completely in the wrong side of both separating hyperplane and also the margin. And then, in other words, sorry, here not both support vector. Here should be the margin. So in this case, we will have what? We'll have the penalty to be greater than 1. In other words, by enforcing a big penalty, I try to ask the model not to do it. In other words, I will ask the model, hey, pay attention to those kind of misclassification points. Try to find a system of the separating hyperplane and the margin such that misclassification will not happen. Okay, so this is corresponding to the cases here. Let's say consider x2 and x3 and x1. So you can see these two training points are completely in the wrong side of the separating hyperplane, meaning that they are misclassified. They will be misclassified. Okay, the thing is, well, all these ideas looks great, CASI, but how would you include the CASI into our SVM model here? Indeed, we can formulate in this way. So in the objective function, first, we add another term, which is C plus summation of the CASI. Of course, here, I forgot to say one thing, that all CASIs, by definition, they are greater than or equal to 0. Say, in this case, equal to 0. In this case, greater than 0. In this case, greater than 1. So all the CASIs are greater than or equal to 0. And then I define this C to be the regularization hyperparameter. Remember, in Lasso and Ridge, we do the same thing. We add an alpha here, or I believe in my notation, it's also called a C. So this is to show how important the summation of these CASIs are. So what does it mean? Why do I need to add it? This is because, remember, what we said is I try to find a system which are the margins and the separating hyperplane, such that I do not have those kind of like no matter misclassification or the case that they are correctly classified but it's inside the margin. I try not to include those points. But how would you try? I mean, how would you guarantee that these things gonna not occur so frequently by this? Because my optimization model is a minimization problem. And all CASIs are greater than or equal to 0. C is also greater than or equal to 0, of course. So this means what? This means, well, if my CASIs are big, it will not let the model to attain the minimum problem, the minimum solution. You know what I mean? I enforce the model is defined to be a minimum problem, and I add these points. This means what? This means I try to push your cassis to be as close to be 0 as possible and give me the optimal solution. That's the point. I try to include all those points in case number 1, which is my cassis are 0, which is all of these things, which is all of this. Everything is well classified in the correct side of my margins. However, excuse me. However, in practice, that's not possible that you have all training day. That's usually not, in most cases, actually not possible to have all training data to be in the correct side of the margin. And if it's not possible, then how can I involve the idea of case B and case C, which is if it's in the correct classification but a wrong margin, I'll make it to be between 0 and 1. And if it's misclassification, I'll make it to be the penalty to be greater than 1. Okay, here we go. Again, cassis I means the penalty for training data I. I will write the main constraint to be this way. Remember, before in the hard SVM, we write it to be this one, right? So the only difference is that I make it the right-hand side to be 1 minus cassis. Let's see why I only need to include such a small, simple modification. I can really make my 3 rules to come true. So first of all, suppose your data is in this case, which is it's perfectly in the correct side of your margin. Then I don't everything is satisfied. Why? Because by comparison, this one, let me just draw a line. Give me a line here. This one can already be satisfied. In other words, cassis I for data I, cassis I equal to 0 is what is attainable. So if it's attainable, of course, I will set a cassis I to be 0. Why? Because my objective function. Why do I need to include one more cassis I and make my objective function to be bigger if cassis I can be 0? So in other words, as long as they're really in the correct side of the margin, cassis are going to be 0. This is satisfied. This is satisfied. Great. Okay. Now see the case number 2, in which, give me an eraser here. Okay, erase. So in which I have what? I have, let's say x2 and also let's see x4. These are in the correct side of the margin, correct side of the separating hyperplane, but the wrong side of the margin, right? How can I guarantee that it's gonna be the cassis gonna be between 0 and 1? It's because of this. Think about it. To save my life, let's consider class number 2 because the y labels 1. I don't have the time negative 1 both sides. Okay, so now I have y equal to 1. And I have WTXI plus B is greater than or equal to 1 minus cassis I, right? Well, your point is here. That means what? That means the whole right-hand side, 1 minus cassis I, it must be between 0 and 1, right? Because if your 1 minus cassis I is greater than 1, then it will be in this side. It conflicts with my definition that my point here is actually between the correct margin and my separating hyperplane. If you want to make this one, to be here, it must be the right-hand side is between 0 and positive 1. In other words, I have what? In other words, I have this. 1 minus cassis I is less than 0 or less than 1 and greater than 0. And you just move, the points. Then you're gonna immediately get cassis I must be between 0 and 1. Here we go. So this one, again, is satisfied. Finally, the third case, which is eraser. Give me 1 second. Let me move these 2 things here. In the third case, I have, which is completely misclassification. You just consider x1 and x3. These 2 points are completely misclassified. What shall my cassis I be? So think about this. Let's again consider, x3 because it's in this direction. Sorry, let's consider x2. Sorry, this direction. So my this x1. So my y1 equal to 1. So here's 1. You have WT x1 plus b is greater than or equal to 1 minus cassis 1. Question: what should 1 minus cassis 1 be? Can I set up, let's say, 1 minus cassis I to be greater than 0? I cannot, because if 1 minus cassis I is greater than 0, your x1 cannot be here. Your x1 must be in this side.
The truth, however, now is that your x1 is here in the left side of the separating hyperplane. That means what? That means the right-hand side, which is 1 minus c1, must be what? Less than 0. And hence, your x1 point can be here. So we just solve it. 1 minus c1 less, here we can, without the loss of generality, we call it xci is less than 0. And hence, my xci is greater than 1. You see what I mean? And again, great, this one's satisfied again. In other words, by such a super simple change, which is give me a razor. Oh my goodness, the system is so difficult. Okay, which is I just change the right hand side from 1 to 1 minus ci, and also I add this penalty, the distance penalty here, in the objective function to be c times sigma summation of all xi's. Immediately, what? This model satisfied all my requirements here, which is again, if the panel, if it's in the correct, if the points are in the correct direction of my margin 1, it's going to be 0. If it's between the correct margin and the separating hyperplane, the penalty should be between 0 and 1. And if it's misclassification, in other words, it is across my separating hyperplane, the penalty going to be greater than 1. And if possible, of course, the penalty will be as small, the penalty is going to be pushed as small as possible, meaning that it's going to push my penalty to be 0. Why? Because my function, my objective function is a minimization problem. And all these C and CIs are positive, are non-negative. So it will try to get as small as possible. And this model, we call it the model of soft margin SVM for 2 classes, of course. And by comparison, our original SVM model is called hard margin. The hard margin means what? Hard margin means you can consider it like a wall. I do not allow any points to cross inside. So it's a hard margin. So clearly, in our real life, soft margin is applied, because in the real training data, it's almost impossible for you to see some cases that, everything is perfectly defined, that no points going to be misclassified or no points are going to be, across the margins. No, you cannot find the solution. And and that's why if you brutally use the hard margin in many training data, you will see there's no solution. By comparison, there's no solution means meaningless. So what's the point to apply machine learning, right? And also, if there's a solution, you may really doubt, hey, is there an overfitting? Is something wrong? But in software, as a soft margin SVM, yes, it's well applied that you can use soft margin SVM in many, many cases. So that's the thing. And so another chain modification is in the definition that we will no longer call like here the hard margin, the points on the margin are called support vectors. But here, no, all the points inside, including on the margins, will be called support vectors. So for example, here x1, 2, 3, 4. Actually should include this point as well. Yeah, I somewhat should remove this point. So otherwise, this point is going to be involved as support vectors as well. So all these things inside or on the margins is going to be called support vectors. Then the next question, which is the final question, how can we make a decision if, after training the model and I'm given a new data, a target data X. So suppose your solutions are W star, B star, and C star. For the new data, again, I just plug in everything. If I will, wait a minute. Yes, here, although I have the cassette, but it doesn't matter because I do have the separating hyperplane. And in my decision, I don't have to involve the cassette anymore. In my decision, I just have the WTX X W star TX plus B star. Again, I'm gonna see whether the point gonna be in the left side or right side of my separating hyperplane. If it's in the left side, in other words, my fx gonna be less than 0, less than 0, then the data gonna be class 1. And if my fx is greater than 0, in other words, it's in the right side of my separating hyperplane, then the class of the target data x is gonna be class 2. So that's the thing. People may ask, since your final decision, it doesn't matter what's your cassette. So what's the point for me to involve cassette? Because by involving the cassette, you can train the good W and the B. You know what I mean? That's the meaning. with different, if you don't have the Kasi, your W and B may even not exist because there could be no solution. But with this Kasi, I can train the correct W and B. That's the meaning why I still need to include the Kasi in my model, even if when finally I make a decision, the Kasi is not, showed here, included here. So that's the point. And then another thing I want to mention is about the C. I mean, how can we choose C? Or let's say a bigger or small C, what's going to be the difference? Well, if I have wait a minute. If I have a bigger C here, means what? My penalty to those kind of errors are pretty big. Errors means no matter the points are in the in the middle between the separating hyperplane and the margins or misclassification. So in this case, my model will what? Will try to be conservative, meaning that the distance of my separating hyperplane, the distance between the two margins is going to try to be small. Why? Because having a small, distance of the margins, I will try to exclude those kind of error points. You know what I mean? Suppose consider here's my two margins, right? And by comparison, let me use let me plot two lines. Let me use the color to be, let's say, yellow color. By comparison, if I have the margin like this way, if I margin in this way, so you will see what you will see. This point, this point, this point, this point, four more points. Let me plot it. Let me just this, no, this one's already there. This. I will include the four more those kind of troublesome points in which my Kasi gonna be greater than 0 instead of being 0, right? And then if you plug in it, you will see what? You will see a bigger objective function. I can actually eliminate these objective functions by what? By choosing my margins to be those two orange colored margins. So I don't have to choose those two. You see what I mean? In other words, a bigger C, a bigger regularization parameter or cost parameter is called, will make my margins to be tight. And then if I have like remove everything. If I have a small C, so my penalty is gonna be smaller. So that you know what, I may try to include those points inside. So you may say, why do you want to include those points inside? Isn't it you will still increase this part? True. Although I will increase this part, but this part could be smaller. I have more freedom to choose my W's such that I may be able to choose a W, the variance, sorry, the distance, the norm square will be smaller. I have more freedom to choose this point. And hence a small C gonna give a relatively bigger margin. You just compare these two. Here, big C, small margin, small C, big margin. So these are the things. And then remember here in all, from all the slides from here to here, we're all talking about what? All talking about SVM model for two classes. But in the real life, well, I can have many different classes, right? How can we do it? So for SVM, there are two popular modeling methods called one against all model or one against one model. But the basic idea is that I consider the so-called M classes to always be two classes, one versus all or one versus one. Okay, so here is a one against all SVM model, which is I consider K to be my current class, and then I'm gonna model the SVM for K versus all other classes. So the objective function is the same, but be careful, I have the CKI, meaning the penalty for class K. Okay, now I have two constraints. First constraint is for y equal to K. In other words, those all the training data in class K. So I have this one. So this one is similar. This one is similar to the previous one. Where? To the previous one here. Actually, both are similar. The difference is the y's. So you can see this is corresponding to the case that y is equal to 1. And the other one, you're going to change the parameter, going to be y equal to -1. Similar cases. So this is going to be less than or equal to, and here I time -1 both sides. Here going to be negative this, negative this. In other words, what I'm doing here is that I consider this case as y equal to 1, meaning that yes, my data is in class K. This case is y equal to -1, meaning that it's not in class K. You know what I mean? So again, here, I mean, looks like I have m classes, but for each class K, I consider in K or not in K. So you know what I mean? So it's similar to this two classes, yi is +1 or -1. So, and then I have, of course, for my CK greater than or equal to 0. So that's the thing. And be very, very careful how many submodels I have. So for each submodel, I have what? I have I constraints, you know, meaning that the constraint for each data. And this is only one submodel. I have m submodels. Why? Because I have to choose K. You know what I mean? Which one is the K? So for each class, it can be K. Class 1, class 2, class m, everything can be K. So that I have m such models, and in each model, I have n constraints. So that's the thing. And suppose you have solved all these, you know, for each K, you have solved the W star, B star, C star. How can you make a decision? Okay, again, we use the idea, which is the maximum likelihood, which is I calculate the maximum of this one, and give me 1 second. Okay, I'm gonna choose a label which gives me the maximum value of this fx actually. So suppose I for k equal to 1, I have this value, k equal to 2, I have this value, and then until equal to m. So I have m values of this, and then I'm gonna classify the target data x to be the value to be the class which has the maximum such fk label. So in other words, here to predict the class label k, which to predict to the class label k, which has the maximum of this fx. So that's the thing. And it's very, very easy to see that if my m equal to 2, meaning that I have only 2 classes, then immediately this model is equivalent to this soft margin SVM model for 2 classes. Okay, so this is a 1 against all model. Another one is 1 against 1 model. So 1 against 1 model is that, well, for total m classes, I just randomly take 2. I take 2 labels, which is K and L. And then for this K label, K and L, for these 2 labels, I'm gonna do this. I only consider points in this, I only consider training data with these 2 labels. So for training data, which are in class K, I have this. For training data, which are in class L, I have this. Or if they are not in K nor L, then I don't have to include these constraints. The problem, so this is one submodel. The problem is how many submodels do you have? I have M choose 2 to be the K and L, right? So I have M choose 2 such submodels. And then, I solve W and WKL and the BKL for each of these submodels. And suppose I get the optimal solution for each of these submodels, denoting them to be WKL star, BKL star, CKL star. How to make a decision for a given X. Be careful here. you cannot like what we did before. Oh, I just calculate FK and then make it to be a maximum FK. No, you cannot do it. You know why? Because here it's pairs. You don't have one for like all the classes anymore. And hence we are gonna have a voting system. The voting system is this. So the voting score of class K gonna be added by 1 if this one is less than 0. And if it's greater than 0, then we're gonna we're gonna add the voting score of class L by 1, which means L plus plus. This is K plus plus. So I just need to plug in this KL star, and then I'm gonna see whether it's bigger than 0 or less than 0, and then to see which one L gonna be increase the store by 1, or K will increase the store by 1. And then finally we predict the label of X by the highest score in the voting system. So SK is my final score of class K. So I will have for the data of X, I will have different scores of these M classes, S1, S2 until SM. each represents the score. I'm gonna label data X to the class that have the highest voting score. So this is the meaning, this is the point of 1 against 1 model. And again, when m equals to 2, it's easy to see that this system plus voting score is equivalent to this soft margin SVM. Okay, so this is all against 1 and all against 1 and 1 against 1 model. Actually, from the introduction, I guess many of you have already realized that it's pretty troublesome, right? The truth is, yes, SVM works very, very well. It's super strong, powerful in 2 classes. But if I have many classes, especially if m is a big number, say suppose I have 1,000 classes, the performance of SVM may not be as good as some other models, especially like KNN. KNN is extremely simple and powerful because you have so many those kind of submodels, no matter for 1 against all or 1 against 1 model, which will make your solution, your computing, computing requirement very high. It will take you a long time to compute those optimal solutions. Although finally, no matter this one or this one, the decision progress is pretty simple, but the computation for all these parameters will take you a long time, and hence SVM are very widely applied in like a low dimension or low class classifications with low number of labels. Let's say m equal to 2, m equal to 3, easy. But if m equal to 2,000, 2 million, then SVM is not that widely applied. So this is all the things for linear classification. The problem is, what if I have data like this way? Say class 1 is this, class 2 is this, even if I have only 2 classes. Well, the original data is like this way. No matter you use a soft margin or hard margin SVM, it will be always like this way. Why? Because we give the model, the operation of the models to be WT plus B equal to 0. That means what? That means no matter what, it's a linear function. It's a line on a 2D. But what if we can kind of like, make my classification like this way? So our separating hyperplane is going to be kind of a curve, and the 2 margins going to also be curve. How can we make it? Yes, we can make it. Actually, we just need to use the kernel function, the so-called kernel trick or kernel technique. So how can we make it? First of all, we can write the dual. Here actually includes a lot of techniques of optimization. So here we can write the dual of the soft margin SVM. To save my life, I only discuss the case for 2 classes, the Lagrange dual, and then I believe first of all you can write the Lagrange dual. Then after the Lagrange dual, you will see that the SVM, the axis gonna be the training model axis gonna be showed as a pair of inner product. And the inner product, of this can actually be replaced by HX and HXI and HXJ. In other words, instead of X, I'm gonna make a function of X, and this is called the kernel function HX. And by the way, original definition of kernel function is this HX. However, because they always, they only appear here in terms of inner product, so I can simply define the kernel function to be the inner product itself. I know many of you may get very confused here. What do you mean by the Lagrange dual, and how can I write this function, this model, to be equivalently to being this model? And indeed, I do have the things here. Let me see here. So let me see which section I forgot. Here I did show a section 2.2. Section 2.2 is 2.1, 2.2 here. Okay, so here's a dual presentation, because remember, before we said that we do want to keep this a half, and we want to make it to, to be inverse, to be, so something is kind of like we want to maximize the R, so which is the distance. Now I want to formulate it to be minimized 1 over R because of here. Here it's going to be quadratic function, and I can have the KKT conditions. Quadratic means it's convex, and hence the KKT condition is going to be both a necessary and a sufficient condition. And it just, well, another thing is called KKT conditions. I don't know whether I included this or not. But if you're not familiar with that, you can simply skip it, or you can just search KKT conditions. But the big idea is that it can be proved that this model and this model, they're equivalent. So the thing here as well, what is that? I can close it. This model, the original soft margin SVM model, and our model with the Lagrange dual, these two are equivalent. And hence, I first modify this x to be hx. Then, because they appear in terms of the inner product, so I directly claim this to be the kernel function. And we usually have four very typical popular kernel functions. The first is the RBF, which is Gaussian kernel, and the second one is the linear kernel. The third one is polynomial kernel, and the last one is sigmoid. And in neural network, it uses a lot, use tangent H models, tangent H function to be the function here. So these are all the mathematical model part of the SVM. Now, due to the time limit, I will have to stop here. In the next class, I will show how to apply SVM in Python using scikit-learn. Excuse me, that's everything about today's class. Thank you very much.